So hopefully this is going to be a quick little tutorial about how we're going to integrate polynomial style functions. Okay, integrate polynomial style functions. So just to remind us what an integral is, right? Integral and anti-differentiation kind of go hand in hand. So if I had a function of type x to the a power, right? This is a base of x raised to some exponents. And I were to take the derivative of this, that would be a times x to the a minus 1 power. Right? When we take the derivative of a powered function, you subtract 1 from that exponent. Okay? Every time we take a derivative, you get a 1 less higher power function. So if you were taking the derivative of, say, x squared, yes, then our derivative would be 2 times x to the 2 minus 1, or the first power. Okay, and of course, nobody ever writes the first power because everything is raised to the first power. Okay, so that's kind of what we look at when we're taking a derivative. Well, what if our function were already x to the a power? Right? What if that's your derivative? What if that's your derivative? Okay? The opposite of a derivative is an antiderivative. So where did that come from? Okay, what is the antiderivative if we have x to the a as our derivative function? Okay? So we're going to kind of undo our derivatives. So our derivatives said we had to subtract 1 from the power. Right? We subtracted 1 from the power. So if we're going to undo our derivative, that means we have to add 1 to our power. A plus 1. So we add 1 to the power of whatever your function happens to be in your integral, sometimes called your integrand. Okay, but then in order to make it balance out, we also have to divide by that new power. Okay, so not only do we raise the power to the plus 1, we add 1 to the power of our original function there, we also divide by that power in order to stay balanced. So that if and when we were to derive it again, we would get the same thing that we started with. So as a random non-specific example, what if f prime was 4x squared? 4x squared is the derivative of some function. Okay, what could that function be? So according to our rules of differentiation or antiderivatives, we would do 4x to the 2 plus 1 or the third power divided by 3. 2 plus 1 to the third divided by 3, which we could simplify as 4/3 of x cubed. Something of that nature. Okay? Very good. What if I had a derivative that happened to be the square root of x? Okay, so the derivative of some function is root x. Okay, what did that function start out as? That's our question. So we're going to apply our rules. So first, we're going to change our radical into a power. Right? If we're going to assign this polynomial rule, then it has to look like a polynomial, which means it can't have a radical. It has to be raised to a power. So here we have the 1/2 power, which represents the square root to the second root. Okay, so applying our rule, we're going to add 1 to our power. So 1/2 plus 1 is 3/2.
Oh, you just made it. You just switched that.
Dividing by 3/2. Okay, now hopefully we all learned in the 5th grade that whenever we divide by a fraction, that's the same as multiplying by the reciprocal. So I take my 3/2 and I reciprocate it to 2/3 times x to the 3/2 power. Okay, so hopefully that's some pretty basic stuff, and your brain is getting in tune with this rule. The rule of polynomial anti-differentiation. So let's take a picture of some problems and see how we can handle those ones. Okay, so here's a variety of problems from our worksheet that we're working with in class today. Okay, so here we have the integral of the third root of x plus 3 dx. Okay, if we're going to use our polynomial rule, we have to first change our radical into a power. So this is the third root, or the 1/3 power, plus 3 dx. So let's use our rules of polynomial anti-differentiation. So we're going to add 1 to our power. 1/3 plus 1 is?
2/3.
4/3. 4/3, right? It's 3/3 is 1. So we add 3/3 to 1/3 and get 4/3. And we also divide by 4/3. Plus, what about our constant 3? Right? This is times x to the 0, because x to the 0 is 1, because we need to have an x in there. What if we add 1 to 0? We're going to get 3x to the first power. Okay? And of course, we don't have to write to the first power, because everything is raised to the first power, so it doesn't make any sense to do that. So our last step is to multiply by our reciprocal, and we end up with
3/4 x to the 4/3 plus 3x.
plus 3x. Okay, and then plus some random c, right? We're always going to have a plus c when we anti-differentiate, because our plus c will be a constant, and when we derive the constant part, it will go away from our function. Okay, let's move over. Hopefully this one will be pretty not difficult for you to do. Pretty straightforward. Okay, so we have 2 times x. So we're going to add 1 to the power, right? So this is already x to the first power, which means 1 plus 1 is 2, divided by 2, because whatever our power is for your antiderivative, your base is also, minus 3x to the third power divided by 3, right? Plus some random constant that we can find with an initial value, which we're not given, so it just leaves it like that. So now simplifying, 2 divides by 2, that just gives us 1. 3 divides by 3, that just gives us 1. So x squared minus x cubed plus some constant c. Okay?
It's gonna get harder. It's gonna get crazy hard.
We never can tell what's going to happen. So on number 3, before we take the antiderivative, we want to distribute so that it's just one polynomial if possible. Okay, so we're going to distribute into this, and we're going to actually take the integral of 2x to the 4th power plus 3x to the 3rd power. Okay, we are multiplying so that we don't have a product. Okay, we only want to integrate one polynomial if possible. So using our rules, we're going to add 1 to our power. So we have 2x to the 5th and divide it by 5. Plus, we'll add 1 to our power here. 3 plus 1 is 4. So 3x to the 4th divided by 4. And then, of course, some random plus c, some constant that we will find when I give you an initial value. We can't find that c without knowing a point on our function. Okay, and since nothing simplifies, this would be your integral. Okay, looking just like that. So let's jump down here to number 5. This one looks like it can be more tricky-ish. And the more tricky-ish ones are the ones that we struggle with the most. So, more tricky-ish. Right, so the first thing we have to do is write these things as powers. Okay, so we need to change our radicals into powers so we can use the polynomial rule of anti-differentiation. So the root x becomes x to the 1/2 power, and only this part of our thing is raised to a power. Okay, so we have 1 over 2 times x to the 1/2, or rather, yes, 2 times x to the 1/2. But we don't want to have that power in the denominator, so how do we get it out of the denominator? by making it a negative power. Okay, so this is going to be 1/2 times x to the negative 1/2. Okay, we don't want to anti-differentiate in a denominator if we can help it. So we change our positive power in the denominator into a negative power in the numerator. And now we can apply our polynomial rule. Okay, so let's add 1/2, or rather 1 to 1/2. When we add 1 to 1/2, we get 3/2 divided by 3/2 plus your 1/2, right? This is always a constant, so it remains a constant. We're going to add 1 to negative 1/2, which becomes a positive 1/2. And we're going to divide this by positive 1/2. Of course, plus c. So now let's do some simplifying. What happens when we reciprocate? Dividing by a fraction, we're going to reciprocate our 3/2 and get 2/3 times x to the 3/2 plus, when we reciprocate 1/2, we're multiplying by 2/1. So 2/1 times 1/2 is just 1. So then we don't have any coefficient in front of our x to the 1/2. So this would be your final antiderivative of your beginning integral up there of root x plus 1/2 root x. Okay, not that it's fun, but you have to take this piece by piece. Like Legos. Piece by piece, one brick at a time. So looking at number 6, piece by piece. Okay, there's a little rule in 5th grade that says if we have a sum in the numerator under a single denominator, we can separate this into 3 separate fractions. So we can do 3x squared over x cubed minus 2x over x cubed plus 3 over x cubed dx. Okay, that is perfectly mathematically legal to do. Because now I'm just going to simplify my exponents like you did in Algebra 1 and also Algebra 2. So if I had x squared on top and x cubed on the bottom, 2 of these can cancel out with 2 of those, leaving me 1x on the bottom. But remember, we don't want to have x's on the bottom. We want to make them into negative powers. So this is 3x to the negative 1. Okay, we could have also done, since we have a fraction, it's subtraction, right? It's the numerator x squared minus the denominator cubed. This is part of your exponential rules, that if you're dividing exponents or exponentials with the same bases, you subtract the powers. Okay, minus 2. Once again, this is x to the first power minus 3, right? 1 minus 3. So this is 2x to the negative 2. Plus, well, this is x to the 0, so that's just 3x to the negative 3. Okay, and this is why calculus is hard, because most of it is algebra. And you have forgotten your algebra, because who uses algebra? Exactly. Nobody.
Who uses this though?
Okay. So now we want to take our rules of integration, or polynomial integration, and apply it to this. Okay, I keep saying integration and anti-differentiation. They're basically the same thing. Okay, so we're taking the antiderivative. So our rule is we add 1 to the exponent. Right, we add 1 to the exponent and we get 3x to the 0 divided by 0. Okay, minus 2, we add 1 to the exponent. Negative 2 plus 1 is negative 1. Plus 3, we add 1 to the exponent, and we get negative 2. Okay, so this is 2 over x when we simplify it, and this is 3 over x squared when we simplify it. But what's happening with this thing? Anything divided by 0 is undefined. So we have to come to grips with what is going on here. Okay? Because this doesn't fit the mold of our polynomial antidifferentiation. Right? This is something different, which means it's not going to be treated like all the other things. Gracias to my students. They have enlightened me of a forgotten thing. And that is, in my rules, I have to divide this by -1 and divide this by -2. So this would actually be a plus 2 over x and a minus 3 over 2x squared. Okay, when those ones become simplified. But we still have to deal with this 3x to the 0 over 0. Okay? There's nothing in our polynomials that help us do that. So let's go back up here and think inside of the box for a little bit. And remember, what does it mean to have x to the negative first power? Okay, that means that x goes in the denominator. So if we think about it, what is the function whose derivative is 3 over x? Right? What function has a derivative of 3 over x? Okay, so hopefully you know that if your function is natural log x, then the derivative is 1 over x. Okay, so whenever we encounter this 3x or the x to the 0 business, okay, we're going to be instead using the natural log rather than some undefined function. Okay, this is the thing that is strange, that doesn't fit the normal pattern. So if I have 3 over x, that's 3 times 1 over x. So this is actually going to be 3 times the natural log of x. That's what the antiderivative of 3 over x happens to be. Okay, and of course, plus c. So if something doesn't fit the pattern, doesn't fit the mold, right, this 3x to the 0 over 0 business, we have to find a different way to do it. Okay, so it doesn't always fit nicely into our box. Here we have to use the natural log antiderivative or derivative, which is a fraction 1 over x. Okay, so that happens sometimes. You just have to make it work. Okay, there's lots more problems that we could do, but I think we're going to stop there just for today. Okay, so these are polynomials. Take your radicals and change it into fractional powers. Add 1 to your power and then divide by that new power. Okay, hopefully this made you smarter.